Now in the past two lessons, we have looked at the concept of mole. In particular, how do we determine the number of moles of a substance given either the mass, the number of particles, the volume of a gas, and the volume of a solution. Now for this lesson, we're going to move away from mole for a while, but rather we're going to focus on mass of a substance. In particular, we're going to look at for a compound, how can we determine the percentage by mass of an element in a compound. Now before I go into the lesson, just a friendly warning that this lesson requires parental guidance because there's going to be some tearing of limbs, pulling out of hands and legs. So if you find that scary, maybe you can find a trusted adult, or you can grab your soft toy to watch the video with you. Okay, so as mentioned, there's going to be some tearing of limbs. Now let's approach this problem as a purely mathematical problem. Okay, so you're given a Lego man, you're given the mass of a Lego man, and you're given the mass of one arm of a Lego man. So the question requires you to find what is the percentage by mass of arms in Lego man. Okay, I'll give you about 5 seconds to digest the question and then see whether you can come up with the answer. Now most of you should be able to come up with the answer as percentage by mass of arms is actually equals to 0.1 times 2 divided by 4 times 100%. Okay, that will give us a value of 5%. Okay, now from this question we can see that in order to find the percentage by mass of a part of a whole, alright, we need 3 pieces of information. First thing, we need the mass of the part that we are interested in, which is your arms. Second thing, we need the mass of the whole. Okay, that means the whole Lego man. And lastly, we need the number of the parts. Okay, so please keep that in mind when we extrapolate this to a chemistry example. Alright, to find the percentage by mass of a part, we need to know 3 things. We need to know the mass of the part, we need to know the mass of the whole, and we need to know the number of the parts. Now in this chemistry example, we are going to find out the percentage by mass of hydrogen present in hydrogen peroxide. Okay, so to recap, we need to find 3 things. We need to find the mass of the part. The part now is your hydrogen. Okay, we need to find the mass of the whole thing. The whole thing is your hydrogen peroxide. And then we need to find the number of your parts, which is your number of hydrogens in the whole. Alright, so if you can find these 3 pieces of information, I'm sure you will be able to apply the same formula as before to find the percentage by mass of hydrogen. Alright, so let's do it step by step. The mass of hydrogen is 1. Okay, you can find that from the periodic table. Mass of hydrogen peroxide is 2 times 1 plus 16 times 2. Alright, that will give you 34. Alright, and if you look at the formula of hydrogen peroxide, there are 2 hydrogens in each hydrogen peroxide. Okay, so with the 3 pieces of information, we can now find percentage by mass of hydrogen, and is equals to 2 times 1 divided by 34 times 100%. Okay, that will give us a value of 5.9%. Okay, now let's go back to our Lego man. Alright, so this question is slightly different. Unlike the previous question where you want to find percentage by mass of the arms, this question requires you to find the percentage by mass of the rest of the body. Alright, so how do we do that? Okay, the most direct method, okay, would be to find the mass of the rest of the body. Alright, so percentage by mass of rest of body is equals to the mass of the rest of the body, which is 4 minus 2 times 0.1. Okay, and you divide by the mass of the whole times 100%. Okay, that will give you 95%. Okay, this is the most direct method to find the percentage by mass of the rest of the body, right? But there's actually a very there's actually a shortcut to finding the answer to this question. Alright, and that requires you to just see that the mass of arms plus the mass of the rest of the body adds up to 100% of the mass. Okay, since the body is made up of arms and the rest of the body, alright, so the percentage by mass of rest of body is simply 100% minus the mass of arms, which is 5%, and that will give us 95%. Right, so there's no need to find the mass of the rest of the body. You can just take the 100% minus the percentage of the mass of arms. Now let's try to put that into the chemistry example now. So in this question, instead of finding the percentage by mass of hydrogen, we are finding the percentage by mass of oxygen. Okay, so the shortcut to solving this question is to recognize that hydrogen and oxygen makes up 100% of hydrogen peroxide. Alright, so I'm going to show you the shortcut method first before I show you the traditional method. Alright, so if you can recall the shortcut method, percentage by mass of oxygen is actually just equals to 100% minus the percentage by mass of hydrogen. Okay, and previously we have found out that percentage by mass of hydrogen is 6.9%. So that will give us a percentage by mass of oxygen to be 94.1%. Alright, this is the shortcut method. Right, for those of you who prefer the traditional method, first you need 3 pieces of information. You need the mass of part, which is mass of oxygen. Second, you need the mass of whole, which is the mass of hydrogen peroxide. And lastly, you need the number of parts, which is number of oxygen. Alright, mass of oxygen is 16, mass of hydrogen peroxide we have seen is 34. And if you look at the formula of hydrogen peroxide, for each unit of hydrogen peroxide, we have 2 oxygens. Okay, so if we apply the formula again, percentage by mass of oxygen is equals to the number of parts times the mass of part divided by the mass of whole times 100%. And that will give us the same answer, which is 94.1%. Okay, now for one last time we will look at the example of the Lego man, and after this point there will not be any tearing of limbs anymore. Okay, so over here they instead of looking at percentage by mass of arms or legs, we are now looking at a combination, which is the mass of limbs. So what exactly defines a limb is the arm plus leg. Okay, so now again we need the 3 things. We need the mass of part, which is mass of limbs. Okay, we need the mass of whole, which is the mass of Lego man. And then we need the number of limbs. Okay, so once we have these 3 pieces of information, we can find the percentage by mass of limbs to be equals to 2 times 0.1 plus 0.2. That is the mass of 1 arm plus 1 leg. Alright, but in Lego Man there are 2 arms and 2 legs, so we need to multiply by 2 divided by mass of whole times 100%. Okay, and that will give us 15%. Okay, so why are we looking at this example? It's because sometimes when we calculate percentage by mass, we don't just look at an element, right? We can look at the component of a compound. Okay, we're going to look at the example in the next slide. So in this case, they are asking for the percentage of water in copper 2 sulfate. Okay, don't get thrown off by this. The method is still the same. Alright, we need to look for the 3 pieces of information. We need to look at the mass of the part. So in this case, we are looking at the mass of water because we want to find percentage by mass of water. Okay, we need the mass of whole, which is your copper sulfate, hydrated copper sulfate. Okay, and lastly, number of parts, which is number of water. Okay, so let's try to solve the question. Mass of water is 16 plus 2, so 18. Mass of whole copper is 64 plus 32 times 16 times, plus 16 times 4. Okay, and then plus 5 times 18. Alright, so the dot over here simply means that we add the mass of the entire water of crystallization to the whole crystal. Okay, and then the last that will give us a value of 250. And then lastly, we need to know the number of water molecules in 1 unit of hydrated copper 2 sulfate. And if you look at the formula, that will be 5. Okay, so for each formula unit of copper 2 sulfate, we have 5 water molecules attached to it. Alright, so again, the method of finding percentage by mass is the same. So percentage by mass of water is equals to number of water times mass of water divided by total mass times 100%, and that will give us a value of 36%. Okay, so once again, it is a good practice to leave your answers to 3SF. Now we'll look at one last practice question for percentage by mass. In this question, we are looking at the percentage by mass of potassium. So we're looking at just one element in potassium carbonate. Okay, so again, very quickly, we find the 3 pieces of information required: mass of potassium carbonate, and then lastly, the number of potassium. Alright, mass of potassium is 39. Mass of potassium carbonate, 39 times 2 plus 12 plus 16 times 3. And then lastly, the number of potassium would be 2. Alright, so if you look at the formula of potassium carbonate, for each formula unit of potassium carbonate, there are 2 potassium ions in there. Alright, so percentage by mass of potassium will be equals to 2 times 39 divided by the total mass of potassium carbonate. Okay, times 100%, and that will give us a value of 56.5%. Now that we have learned how to determine percentage by mass of an element in a substance, we are going to see that we can actually use this mass data to help us predict the molecular and empirical formula of a substance. Alright, so first thing, we need to define the 2 terms, empirical and molecular formula. Alright, so if we look at the 2 compounds given in this slide, right, one of them is phosphorus pentoxide, the other one is glucose. how do we obtain the molecular formula? Molecular formula, to get the molecular formula of a compound or a molecule, we simply need to count the total number of atoms of each element in that molecule. Alright, so if you were to count the number of phosphorus and oxygen atoms in phosphorus pentoxide, the molecular formula will be P4O10. Alright, and similarly, if you were to count the total number of carbon, hydrogen and oxygen atoms in glucose, you will get the molecular formula C6H12 and then O6. Alright, so this is the molecular formula. Now what is empirical formula? Empirical formula is the simplest ratio. Okay, the simplest ratio of atoms of the elements in the compound, meaning it is the molecular formula reduced to the simplest ratio. So if we look at the molecular formula of phosphorus pentoxide, can we reduce it to a simpler ratio? Answer is yes, it can be P2O5. Similarly, if we look at the molecular formula of glucose, can we reduce it to the simplest ratio? Yes, it will be CH2O. Alright, so why are we learning this concept of empirical formula? What is empirical? Empirical means obtained from experimental data. Alright, so if we were to conduct experiments to find out how many phosphorus and how many oxygen is present in phosphorus pentoxide, we cannot get the exact number of atoms, but what we can get is the simplest ratio. Alright, meaning we can determine that for every 2 phosphorus atoms there are 5 oxygen atoms. So from experimental data we can only obtain the empirical formula, and then making use of some other data we can then obtain the molecular formula. So that is why molecular formula reduced to the simplest ratio is known as the empirical, the experimental formula. So as mentioned, molecular formula shows the exact number of atoms of each element in the molecule, whereas an empirical formula shows the simplest ratio of atoms of each element in a molecule. Now there can be molecules where the molecular formula and the empirical formula is actually the same. For example, water. Okay, for water, this is the molecular formula of water. It is already in the simplest ratio, so the empirical formula of water is the same as the molecular formula. Now I'm going to show you how we can obtain the empirical formula of a compound based on the mass data, or based on experimental data. Alright, so in this example we have a sample of copper oxide, okay, which contains 8 grams of copper combined with 1 gram of oxygen. So based on the values given to us, 8 grams of copper combined with 1 gram of oxygen, we can actually determine the empirical formula of this oxide of copper already. How do we do that? We need to construct a table that is going to look like this. So first we write down the 2 elements, or all the elements involved. So we have copper and we have oxygen, and then what are we given? We are given the mass, alright, which is 8 grams of copper combining with 1 gram of oxygen. Alright, so what comes in the next row is this. Alright, you write down the relative atomic mass of the 2 elements. Copper has a relative atomic mass of 64. Oxygen has a relative atomic mass of 16. Alright, so next we can find number of moles of each element present. Okay, how do we get number of moles from mass and atomic mass? Is to take mass divided by the atomic mass. Alright, that will give us, and then this is 0.0625. Alright, so after finding number of moles of copper and number of moles of oxygen, in order to get the empirical formula, we need to get the ratio of the two. And how do we get the ratio? Is to identify the smaller or the smallest, the element with the smallest number of moles, which is this. Alright, and to find the ratio, all we need to do is to divide all the number of moles by the smallest number there. Alright, and that will give us a ratio of 2:1. Alright, so from the ratio of 2:1, we can conclude that the empirical formula of copper, the oxide of copper, is actually Cu2. That means there are 2 copper atoms combined with 1 oxygen atom. So this is the empirical formula. Alright, now we're going to use this method to look at a few other questions regarding mass data. So in this question now, we have a compound that's made up of 3 elements. You have barium, titanium, and oxygen. Okay, so and one other difference between this question and the one before is now you are not given the absolute mass of the elements. That means not in grams, but you are given in percentages. Alright, 58.8% of barium, 20.6% of titanium, and 20.6% of oxygen. So how do we handle percentages? When you're given mass data in terms of percentages, the trick to converting to mass is this. You can do this for 100 grams of substance. Alright, so for 100 grams of substance, mass of barium, titanium, oxygen, again you write down the 3 elements involved, or all the elements involved. For 100 grams of substance, if 58.8% of it is barium, I will have 58.8 grams of barium. I have 20.6 grams of titanium, and I have 20.6 grams of oxygen. Okay, next I need to write down the relative atomic masses for the different elements. Barium being 137, titanium is 48, and then oxygen is 16. Alright, next we need to find number of moles, right, which is mass over molar mass, or mass over relative mass. So and then I will get the number of moles, which is 0.429. Okay, now that I've found number of moles of barium, titanium, and oxygen, the last thing that's left to be done is to find the ratio. Alright, and how do we find the ratio? Again, is to look for the smallest number in there and divide everything by the smallest number. In this case, the smallest number is 0.429. Okay, so the ratio would be and if you were to compute it correctly, it will be 1, 1, and 3. Alright, so the ratio of barium to titanium to oxygen is 1:1:3. That would mean that the empirical formula is BaTiO3. Okay, 1 barium, 1 titanium, and 3 oxygen. Okay, up till now we have seen examples of how we can get empirical formula from the mass data, from experimental mass data. We have yet to see how we can find the molecular formula, which we will see in the next example. So in this example, we're given the mass data of a compound which is some iron chloride, and we're supposed to find the empirical and molecular formula for the compound. Alright, so the elements involved would be iron and chlorine, and the first thing that we need to find is the mass of both. Alright, what makes this question even trickier is that we seem to be only seem to be given the mass of chlorine. What about iron? I mean, if you can think of the compound iron chloride, alright, if 65.5% of it is chlorine, what is the rest of it? It has to be iron. Alright, so we don't need to have the percentage of iron given in the question. We can find it by taking 100 divided by 65.5, and since again is given in percentage, we can convert it to mass by simply writing 400 grams of compound. We have 65.5 grams of chlorine, and we have 34.5 grams of iron. The next step, we have to write down the relative atomic mass of iron and chlorine. So iron is 56 and chlorine is 35.5. Next, we have to find number of moles, which is to take mass divided by molar mass. I'm going to write down the number straight away. Okay, and then lastly, we need to find the ratio of iron to chlorine, and this one is quite simple. We just need to divide by the smallest number again, and we'll get 1:3. Right, so what this means is that in the compound we have 1 iron to 3 chlorine, so that will give us an empirical formula of FeCl3. Okay, so there is a part B to this question. Now part B, you are given the relative molecular mass of the chloride, and using the relative molecular mass, we are supposed to deduce the molecular formula. Remember, in part A we only got the empirical formula. So how do we find the molecular formula given the relative molecular mass? Is this: we need to go back to the definition of empirical and molecular formula. Alright, so once again, molecular formula shows the exact number of atoms of element in a molecule. Empirical formula shows the simplest ratio. So what's the relation between molecular and empirical formula? Is this: is that molecular formula is n times the empirical formula, n being an integer, 1, 2, 3 and so on. Right, and since molecular formula is n times of empirical formula, the molecular mass, alright, the relative molecular mass will also be n times of the mass of your empirical formula. Okay, let's see how we can apply it in the question again. So previously we have found out that the empirical formula is FeCl3. So now, given the relative molecular mass of the chloride, we are supposed to use it to find the molecular formula of the chloride. To do that, we need to recall, in the last slide we learned that molecular formula is n times that of the empirical formula. So to obtain the molecular formula, the first thing we need to do is to find out what is the value of n. And to find the value of n, we need to also recall this, that the molecular mass is actually n times the mass of your empirical formula. Okay, the molecular mass is given in the question as 325 over here, equals to n times the mass of your empirical formula, which is FeCl3. So the mass is 56 plus 35.5 times 3. Alright, that will give us the following equation. Alright, and that will allow us to determine the value of n to be 2. Right, so what this means is that the molecular formula is actually 2 times the empirical formula. So the molecular formula of the chloride form is actually Fe2Cl6. Okay, so what we have learned in the second half of the lesson is that given mass data of the different elements in the compound, we can actually use it to find the empirical formula of a compound. And once we have found the empirical formula, by comparing the mass of the empirical formula to the actual relative molecular mass, alright, we can actually find how many times is the molecular formula larger than the empirical formula, and from there we can obtain the actual molecular formula of the compound.